So today our speaker is going to be John Thornley. He is an associate and senior geotechnical engineer at Golder Associates Incorporated in Anchorage, Alaska. He has over 14 years of geotechnical and earthquake engineering experience. Recently, John was a co-lead for the EERI Learning from Earthquakes reconnaissance effort for the November 30th, 2018 magnitude 7.1 Anchorage, Alaska earthquake. Currently, John is the chair of the Municipality of Anchorage Geotechnical Advisory Commission, and he has served as a field manager of geotechnical studies and prepared recommendations for a variety of infrastructure projects, including bridges, roads, airports, large liquefied natural gas, water storage tanks, pipelines, wind and cellular towers, and utilities. As a part of John's work across Alaska, he has been involved in seismic hazard studies, seismic site response analyses, planning studies for large infrastructure buildouts, and cold regions and permafrost engineering. His design work includes ground improvement and liquefiable soils, deep and shallow foundations, slope stabilization, retaining structures, and embankments. And I'm gonna go ahead and pass it off to John and let him start his presentation on liquefaction susceptibility of quartz sands. So thanks again, John.
All right, thank you. And just a quick mic check, make sure that you can hear me. Thumbs up or. All right, great. All right. Well, thank you so much for having me here today. I'm very excited to be here virtually. Next time, maybe in person, and we'll kind of leave it at that. This is you see my office in the background. This is the longest I've spent in my office since March last year. So I've been working from home like many of you for the last year. But I came in here earlier. We were having a quick Q&A, and I heard a dog barking in the background. Part of the reason that I'm in my office today. So anyway, thank you again for having me. This is a program that's supported by an endowment from the Friedman family, and really appreciate EERI allowing me to be part of this visiting professionals program. I've got a few slides as some background for EERI that I'll go through quickly, just to give you a little bit of background with EERI in case you're not a member, or you're getting ready to move on from school and wondering what what the benefits of EERI are in your professional life. EERI, was established in 1948, and it's an interesting group of people that are all focused on reducing earthquake risk. And so you can see on the right-hand side, engineers, geoscientists, social scientists, architects, planners, you name it. We're all of the same, under the same umbrella of dedicated to reducing earthquake risk. And so it's not just a bunch of engineers but a variety of disciplines, and it's a really neat organization for that from that matter. The photo here, I'm famous. I'm standing actually right here in this photo. I didn't put this one in, but this is part of the slide pack that EERI puts together. So every time you see this photo, you can say, "Oh, I had a presentation by that guy standing in the back right there." That was an EERI meeting in Anchorage, Alaska, and at that site visit that we're on is looking at school damage related to an earthquake, magnitude 7.1 earthquake. It was part of the Learning from Earthquakes site visit. The mission statement by EERI is advancing science and practice of earthquake engineering, and doing that through a variety of areas. Whether it be social, economic, political, and so on, and then looking at advocating comprehensive and realistic measures to reduce the harmful effects of earthquakes. Why EERI? So it allows you to connect to other people with the same focus as you, learn about the progress and growth in the science of earthquake preparedness and risk mitigation, and then it also allows you to become a leader in the field and rub elbows with the other leaders in this field. little bit about how I got involved with EERI. I was a graduate student with University of Nevada, Reno, and I joined the student chapter there, like many of you on the call today. And we did some activities. We had some folks come and speak in similar fashion to what I'm doing today. But I really liked earthquake spectra, and so I continued my membership after my student days, so that I kept getting that publication. And even to today, I really look forward to the day that shows up in the mailbox. But probably the biggest change with how I really interacted with EERI as a professional and as a person was at the 2010 Haiti earthquake. And a call came out to donate time to take a look at photos of earthquake damage and draw polygons around potentially damaged buildings and help with a virtual assessment of the damage and destruction caused by the earthquake in Haiti. And you know, I spent countless hours over the several days and weeks after the earthquake, combing through photos and drawing polygons around these damaged buildings. And it really kind of brought it home how even though I wasn't able to necessarily respond to the Haiti earthquake in person, this allowed an avenue to help make a difference with supporting earthquake research and also responding to earthquakes. And so that was a really neat piece of or neat opportunity for me to actually interact with EERI in a really positive way and be able to share my time and expertise. Right now, we're in the middle of reinvigorating the Alaska chapter. We do have an Alaska chapter that's a statewide organization with a few different members. It's kind of gone into quiet resting for a little while, but we're reinvigorating, especially after the magnitude 7.1 earthquake we had in 2018. And we're looking at a variety of options and opportunities to leverage EERI's muscle to help make change and advocate change within the politics of Alaska, as well as a variety of other areas to learn from that earthquake in 2018 and be ready and in better position for the next big one, because Alaska is a great place for earthquakes. It's our earthquake laboratory. Have lots of earthquakes every day, and probably, I think, what is it? We have a magnitude 7+ earthquake on average every 11 years, and so plenty of earthquakes to learn from. So who are EERI members? Geoscientists, engineers, architects, social scientists, a variety of disciplines. It's really neat as you go to, say, the annual meetings, you get to rub elbows with a variety of people from different walks of life, and you get to talking and you see how the things that you do impact what they do, and vice versa. And it's a really neat organization from that standpoint. There's also the School Earthquake Safety Initiative, which is focused on making sure that the places that we send our children and attend as well are safe places to work. One of the things that we observed from the November 2018 earthquake in Alaska is that most of our damage to schools was non-structural damage, and luckily through a lot of training and practice, duck cover and hold drills, Anchorage was able to, I think, have one or two very minor medical issues related to the earthquake in the schools. But ceiling tiles fell down, bookshelves fell over. I mean, we had a variety of non-structural damages that were a result of the earthquake that are worth thinking about. And so these school earthquake safety initiatives really help with that. The Learning from Earthquakes program, which I was personally involved with the 2018 earthquake, as a co-author of the Learning from Earthquakes report on that. And that was a really neat opportunity to not only work with EERI, but with teams like GEAR and STEER, GEAR being a Geotechnical Extreme Event Reconnaissance, and STEER and a variety of other groups, USGS, FEMA, and others, and learn as much as we could from the November 2018 earthquake. And you'll see, especially if you're from a structural background, it's that Learning from Earthquakes report is heavily focused on a lot of the structural damage that was observed. So I'd encourage you to take a look at that report. But these Learning from Earthquakes program, this program is a really interesting and a neat program, and I look forward to future opportunities with that. Let's see. So there is one of the highlights and one of the neat opportunities here is the LFE travel study program, which gives you opportunities to actually go out and be sponsored and provided the opportunity to help gather data and be involved with some of your colleagues from around the world. So it's a neat opportunity, and I'd encourage you to take a look at that. Student membership benefits, I probably don't need to tell you, much about that. You have the Friedman Family Visiting Professionals Program, which is what I'm here today to present on. And then the seismic design competition and others, which I've learned Rosie is heading up there. And then travel grants to meetings and access to earthquake spectra and more. So what do you do after graduation? You can join the Student Leadership Council and become a younger member on the Younger Members Committee, of a whole variety of different things that you can do after graduation. And so I'd encourage you to consider that after you graduate as well. Here are some chapters. Here are the regional chapters. You can see Alaska there. Proud to be, Alaska is actually the first EERI chapter. So we had back in 1980s, had some real visionary folks that got the Alaska chapter started up, and so we're proud to be that first chapter and looking to get back into it. San Diego chapter is a really neat one as well. They do a lot of different lecture series. You'll find that each of these regional chapters brings an interesting approach to how you can be involved with EERI. So a little sales pitch. The student members get first year of as a young professional free, and then it's reduced rates for the next 4 years. So that's always good news as you're dealing with student loans and actually you might even have a little bit of money now because you're getting paid a different paycheck than you were as a grad student. But there's some discounts there. So. And then, EERI.org is where you can learn more about the variety of these topics. So with that, we're now, I guess, to the heart of the matter and the presentation today. So today I'm going to talk a little bit about liquefaction characterization and mitigation on a project that I was involved in and led in Kwajalein in the Marshall Islands out in the Pacific Ocean. And so we will just quick cover of the outline where we're going today, kind of a roadmap for today's discussion. We'll have a little bit of a project overview, where the heck is Kwajalein, and get you familiar with where we are in the world. Talk about the seismicity and some of the geotech work that was done, and design efforts for foundation systems, along with then you could call it phase 2 of additional geotechnical exploration, followed by some revised design for this system, and we'll kind of walk through why we had to phase 2, and we'll get there together. All right, so you can see the west coast of the United States here on this little Google Earth image. Alaska is kind of coming down here. Here's Hawaii, and about 2,100 miles west of Hawaii is this little atoll, the atoll of Kwajalein. And Kwajalein is interesting. It was in World War II. It was heavily fought after between the Japanese and the U.S. For control because it is such a unique and strategic location. And there was, I mean, battle after battle after battle at this this atoll for control of it, which is really interesting, especially geotechnically, because you end up one of the biggest hazards on this island was what we call unexploded ordnance, UXO, and so as we prepared for our drilling program, the comment was, well, how do you deal with all of the UXO? And they say there's so much unexploded ordnance at this site that they don't even try to find it anymore. Because when they go through and screen the materials in the upper few feet, they'll screen and they think they have all the UXO, and then it rains and all of a sudden you have more grenades that come out of the material that was screened. So it's it's a little nerve-wracking as you start going and pushing cones in the ground or drilling holes in the ground. All of the unexploded ordnance that is out there. Luckily, our program didn't find any of that, and so we feel feel fortunate for that. But we were working in an area that had been kind of combed through a bit before. So we have this atoll, and we're down at the southern portion of this atoll, kind of out in the middle of nowhere, just a little north of the equator. So on this atoll is an army base. This army base operates under the supervision, if you will. It's a U.S. Army base, but we lease it from the Republic of the Marshall Islands. So this is foreign soil that we're leasing as part of this installation. And so you got a big runway here. There's something called the space fence, which basically is a way to look for missiles being launched around the world, and then some housing and different facilities. And then our project was right here, kind of in the middle, and it's a fuel tank replacement project. So they have a lot of tanks from the 1950s that are old and deteriorating, and this was a project to help replace some of those fuel tanks and get capacity back up to where they wanted to be. Now, I'll say an interesting quip. I don't know how many of you have heard the adage, civil engineers essentially design targets for mechanical engineers. And so you've got mechanical engineers that are more in the missile side of things, and you've got civil engineers that then make the targets for those. Interestingly enough, when I told my father that I was doing a project out at Kwajalein, he said, "Well, that's interesting. I've fired a lot of missiles towards Kwajalein, and as part of the testing, he's a mechanical engineer that used to design warheads." And so it was kind of interesting to have that kind of personal relationship to this trip out to Kwajalein, and truly the civil engineer making the target. So as I said before, this is a fuel tank replacement project. We had a number of large diameter tanks and some horizontal tanks, along with a new filter building and operations building. And then because this was going to be work at an active fuel tank farm, the construction is going to be staged over a number of years as they take one tank offline and put another tank in service. And so that adds a bit of complexity because you're actually working in a site that you can only slowly take apart and rebuild. and that it also affected the ability for us to perform explorations where each tank was going to actually be set. Before we went out there, we had to establish some design criteria for the site, and this is through the U.S. Army Corps of Engineers, and so they have some pretty prescriptive requirements for settlement. Settlement being the big damager of large tanks. So we were allotted less than 2 inches of total settlement, and then less than ½ an inch per 32 feet of circumference around the tank for differential settlement. And one of the interesting pieces was some of the layouts that we looked at as these tank farms or these tanks were being optimally placed would in part overlap with an old tank. And so you have this kind of difference in stress history from one side to the other. That was something that we were keeping in mind. Talking about the seismicity, so you're out here in the middle of the Pacific Ocean, far from any subduction trench or anything like that. But when we started the project, the PGA for the site, site class B PGA was 0.48 G, as prescribed by the U.S. Army Corps. And that was the design requirement that we were held to design for. There was a lot of arguing by different groups that the seismic hazard, you have to have a source for that seismic hazard. And there was a lot of argument whether or not that actually existed. AMEC, among others, had done PSHAs, probably seismic hazard analyses, suggesting that rather than it's 0.48 G, it'd be as low as 0.08 G, which is a big change when you're talking about a liquefaction, especially liquefaction screening analysis, substantial change. And so the USGS and ERDIC came together and they did their own PSHA, and they downgraded the site from 0.48 G to 0.14 G. And that happened as we were getting into the project. So it was well timed for some of the work that we were doing at the site. And so we ended up using 0.14 G for site class B. And when you modify that for a site class D site or F site, you get a 0.21 G site modification. So that was a lot nicer than what we were looking at when we originally started looking at this project. Now a little closer look here, you have these existing tanks that are all there. These are water storage tanks. They actually, because Kwajalein is about 2 to 3 meters above sea level, there's not a lot of ways to get a clean groundwater. So they actually harvest. They harvest their drinking water and the water that they use on the island from the runway, and so they collect all of the rainwater from the runway and collect it in these treatment ponds, which are next to the fuel storage tanks. This little blue line here is the original coastline. So on the right-hand side of the screen is the original Kwajalein Island. And then everything on the left-hand side of that blue line is actually new fill, dredged fill that was placed from hydraulically placed from dredges. And so you have a new island and old island. And as you might imagine, based on our knowledge of hydraulic fills, especially hydraulically placed fills for dams and other structures, they're highly have high potential for liquefaction because they just didn't get the compaction and don't have the relative density that soils need to resist liquefaction. So this is kind of the layout we have, and as I said before, this is an active fuel tank farm, and so we have some borings scattered around the outside of the site, and as well as locations for a new operations building and a filter building. for filtering the fuel as it comes off the barge from the lagoon. Let's see. So let's see, anything else I want to say there? We did get one boring that was kind of close to a tank, because when we were there, this tank had already been removed from service and demolished. So we could actually drill one hole that was kind of close to where a tank was going to be constructed. So as part of the exploration program, we advanced a number of CPTs and SPTs with mud rotary for each of these structures. And then we had a couple of them, for instance, test boring 3, where we did side-by-side CPT and SPT, so that we were able to collect both sets of data from essentially the same soil stratigraphy. We also conducted vertical seismic profiling down to 100 feet to get our seismic site class, and performed some additional other work on site. Looking at a CPT log here, you can see that it actually comes out as a silty sand with the soil behavior index. And you know, with our tip cone resistance and the friction ratio, and you know, everything actually worked out really nicely for that CPT work. We did have a drill out at the top, and that was primarily so that we didn't. We thought it was safer to drill and hit a grenade or other unexploded ordnance than to push the cone through it. Because the cone's a lot more expensive to replace than a drill bit. If something bad happened, we did also lay a 1-inch steel plate down that we drilled through, kind of like a moon hole, so that if we did indeed hit something, the steel plate would take some of that energy out of that device before it impacted our drilling team. So going forward, you know, we had all of this CPT and SPT data. We went through and looked at you know, bearing capacity, settlement, all of the you know, typical things that you do for a fuel tank replacement. We also, you know, performed a liquefaction analysis using you know, several different flavors of SPT and CPT, simplified screening methods, looked at the seismically induced settlements, and when we did that for using our SPT data, our standard penetration data, we ended up with a factor of safety that was pretty much above 1 and nearly 2 in basically all cases. So the SPT data always suggested that the liquefaction hazard was fairly low. However, when we did the same thing with the CPT data, we found that we had a number of locations where liquefaction was actually less than 1. So this green to yellow line, and we ended up with more than 10 inches of vertical settlement estimated at this site related to the liquefaction potential based on the CPT methods. And I should step back and talk a little bit about the island. So this atoll is a coral limestone atoll, and rock is actually quite a bit down, hundreds of feet down below the ground surface. But the sands at Kwajalein are coral sands, and typically with the simplified screening methods, the database of those methods are based on quartz or silica based sands, and so the quartz and silica sands have a much different structure than the coral sands. You know, there's potential cementation with coral sands. There's just the granular structure, and we'll get some pictures of the granular structure of these sands. Actually, I should I could grab I don't know, we can see that. This is a piece of coral from Kwajalein, and you can see, it's your typical coral, right? Fairly high porosity material. Just happen to have that sitting on the desk. It's good that I'm at work today. So, but the thing that caused us a lot of concern was, with the compressibility of these coral sands, did pushing the cone through those coral sands crush the particles and suggest that they're actually less dense than they really are? And is that impacting our ability to estimate the liquefaction the liquefaction potential of these coral sands? And so we have the SPT method, which as geotechs we use when we have to, but we acknowledge that the SPT method is not always the best method to characterize soil from a liquefaction standpoint. And then we have the CPT, the gold standard, if you will, for liquefaction analysis. And so through a number of discussions with the Corps of Engineers, we came to rest on using the CPT data, mostly because it was fairly conservative, at least with respect to, here we have 10 inches of settlement that may result as liquefaction of these coral sands happens. And so as we're looking at that, we went and looked at the difference between SPT methods and CPT methods from a variety of the liquefaction screening methods. And when you look at the SPT methods, you have 0.3 to 7 inches of settlement, up to maybe 2.8 inches of settlement, and you're almost below that 2-inch total settlement threshold, right? Ignoring the fact that the liquefaction screening method is a free field estimate of settlement. Then when you look at the CPT methods, now you're looking at up to 17 inches of settlement, which is hard to believe and hard to agree with necessarily. Seems some of this is this site has been here for a little while. We're not accounting for cementation of the some of the materials, even if it's lightly cemented. But when we look at the CPT option, we end up with fairly large settlements. And so when we looked at the sensitivity to settlement, based on PGA, we found that we had, it didn't take a very large earthquake to actually get 2 inches of total settlement, and certainly much smaller PGA than what our design PGA was. And so this was a helpful graph to have that conversation with the Corps of Engineers on which way we should go down. So then, acknowledging that the site, based on our characterization to date, suggested that we'll have liquefaction at the site. We went through and said, all right, here's a number of mitigation options that we can utilize. We could utilize surcharging, dynamic compaction, rapid impact compaction, deep soil mixing. There's a whole host of options. Some of the limitations, as I mentioned before, we have a tight site with tanks right next to each other. So surcharging, in order to build that surcharge up over top of an area, you'd end up impacting other tanks adjacent. There's containment around those tanks, so they have walls. So if you start deflecting those walls, you affect the containment as well. Dynamic compaction was another one that we were a little worried about with respect to an active tank farm and doing dynamically loading the soil adjacent to pipe racks and other features. Rapid impact compaction wasn't going to get to the depth, the depth of influence that we would need to actually make a difference for mitigating some of the liquefaction. And so at the end of the day, we ended up selecting deep soil mixing for ground improvement. And we developed a number of models where we looked at settlement and impacts of adjacent tanks to each other, new tanks versus old tanks, and so on, and the configurations for those tanks. But at the end of the day, we selected deep soil mixing as the preferred mitigation technique. And so what we ended up doing was we designed a DSM panel system to create cells and reduce the development of pore pressures at depth. And so here's a schematic of what we had in mind, essentially using a cutter soil mixer and cutting in and placing these DSM panels to create these cells. And these DSM panels extended about 50 feet below ground in order to be able to mitigate the liquefaction. And so creating this network of panels down to 50 feet is actually a fairly time-consuming and expensive process. And so there was a lot of discussion, again, back to the origins of our liquefaction hazard and our issue. And so at the end of the day, we selected this option here to go with, and just doing a time check here to make sure I'm all right. I think I'm tracking all right, but only 100 slides to go. I'm just teasing. So fast forward a couple of years, we ended up getting called back out to the site because this is a fairly expensive and time-consuming program, and so there was a new and renewed interest into, are there other options to characterize this soil to take advantage of its potential to be potentially a lower likelihood of liquefaction when compared to your standard silica or quartz sand style screening. And so, and we've been talking about this with the Corps for a number of years, saying, if you want to evaluate this option, we'd be happy to help you do that, and we can put together a laboratory program to help characterize the liquefaction susceptibility of these soils at this site, rather than depending explicitly on a simplified method. So we went out and we performed additional SPT and CPT, and then we also collected soil samples and took part in getting a bunch of buckets shipped back to the U.S. And remember, this is a foreign site, so bringing potentially contaminated and luckily no UXO soils back to U.S. soil took a bit of effort. You can see the screen here, a 3/4 inch screen that I dutifully shook all of these soils over to collect them. I took personal responsibility in collecting these soil samples, mostly for a vacation to Kwajalein, but no. It was a neat trip. I got through the course of this project, I've been out to Kwajalein twice now, and it's about a 7-hour plane ride from Honolulu. So it's a long ways out there, and it takes a bit of time to get out there. So we collected nearly a cubic yard of material, and did some index testing, sieves, mix and minimum and maximum unit weights, specific gravities, carbonate content. We found that the carbonate content, as you might imagine, is nearly 100%. This being coral material. And then one of the first steps that we took on was doing a CPT calibration testing. And so one of our big concerns was, is the is the cone that we used out in the field actually giving us the correct data based on the soils that we have. And so we used a Pagani mini cone, and we did calibration testing in the back of the lab here using a rock drill rig to advance the Pagani cone and push that through soil at different relative densities in our calibration chamber. And I know that a number of Virginia Tech faculty have done cone calibration testing. So if we want to talk about that after, and share, the grief of some of these experiences, happy to do that. But this was a really neat opportunity to just kind of go back to basics on figuring out what the cone is actually telling you. And so it was a fully instrumented cone with tip, skin, and pore pressure measurements that we were able to collect in the pushing of this cone. We also, so we did it at a variety of relative densities. And as you look at the cone resistance at higher relative higher relative density than at a lower relative density, we played around with a number of placement methods for placing the sample or constructing the samples, and ended up with air pluviation as providing kind of our best results. Moist tamping was done. We did a variety of different techniques to come up with sampling. So there was a lot of kind of playing around in the lab for weeks before we settled in on one methodology. And then we ran our actual tests with the cone. We also did track seal testing, undrained and drained track seal testing. Here's a couple. I ended up actually, I'll be honest, I stripped out a number of slides last night as I saw the number of EERI slides at the beginning so that I didn't go too long today. So we won't dive into these too much unless there are questions at the end. But we did track seal testing. We also did bender element testing, looking at the shear wave velocity of the soils at a variety of relative densities. Looking at some of the scanning electron microscope, this is what the grains look like kind of when you're just looking at them in your hand, and then a little closer structure. But then when you look really close in, you can see all of this pore space that's just kind of sitting there. That's much different than when you look at a 30 micrometer sample of a quartz or silica based sand. So that's kind of an important piece of this story, we believe. We also did cyclic direct simple shear testing with a number of cyclic tests and post-monotonic tests as well. And from all of these efforts, we were able to establish a relationship between the relative density and placed relative density, controlled relative density, and the tip resistance from the cone. And one of the big takeaways is you can see the line in blue here tends to be towards the lower relative density, and the line in the red is higher. And what we found through our study is that yes, indeed, the cone was under predicting the relative density of the quadrillane sand when compared to the Pagani cone and known relative densities. So utilizing both that information from the cone testing and then the cyclic and track seal testing, we were able to then look at what actually happens with respect to the cyclic resistance. And so when we plot the cycles to liquefaction, so double amplitude shear strain at 3.75%, as Bean and Jeffries, or Jeffries and Bean, suggests, we found that our magnitude 6 earthquake was roughly 7.5 cycles. We ended up with a cyclic stress ratio of 0.2. And so when you're within this box here, you can anticipate liquefaction. And it's interesting when you plot a typical silica sand, you have this zone of overlap. But when you actually plot the quadrillane sand at 65% and 25% relative density, you actually find that you're well away from the cyclic resistance ratio and the cycles to liquefaction danger box, if you will. And what this actually suggests is you have a higher or a lower likelihood of actually liquefying the soils under the design earthquake. And what this gave us was confidence to reevaluate and apply the methods that we'd used in the simplified screening and adjust the CPT results for our site-specific study. And we're able to look at the liquefaction potential with a new eye focused on quadrillane sands. So we found that the quadrillane sands were much less susceptible to liquefaction. And this was actually found in other studies that we looked at by other folks in published literature that they found for their sites as well. So this and Dr. Green, I can't remember, this was back in 2015, 2016 that we actually looked at this. So I may have looked at one of your papers if it was that far back, but I don't recall offhand. But you know, other coral sands may or may not behave this way, but this was certainly something that we were finding from quadrillane sands. And so is it the porous structure or the angular nature of the particles or something else? But we felt more confident, and it kind of sat better with the gut engineering judgment side of the work than our original 10 to 17 inches of liquefaction induced settlement. So from that, we were able to reevaluate our need for ground improvements, reperformed the liquefaction analysis and looked at the liquefaction induced settlements and others, and then we're able to compare our results back to the design criteria, the original design criteria. So then the question is, you know, is there any room for reducing the depth of ground improvement or any optimization that can be provided? And so just an example plot, we see a general shift in the cyclic resistance ratio, giving us a greater factor of safety than 1 for this specific boring anyway, or CPT. And so we then ended up with a fairly modest settlement with depth. And what that actually looks like when you plot it here, we ended up having settlement. You know, if we improved the upper 25 feet or so, we could control the amount of settlement down to less than 2 inches for our sites, based on using deep soil mixing still. But now we're focused more on static settlement rather than liquefaction induced settlement, which reduced the depth of improvement. It also allowed us to reduce the area replacement ratio. You saw that how tightly those grids were placed for the deep soil mixing. And that ultimately resulted in savings in schedule and cost. So the project is still under construction, so we're looking forward to how this all works out. But at the end of the day, this is the new configuration of the deep soil improvement, and again, it's more related to the near surface settlement aspects rather than liquefaction aspects for the site. So you know, the cost for constructing these kinds of ground improvements under this tank, you know, dramatically are reduced, and as well as the schedule is shortened as well, giving the island of Kwajalein a sure ability to maintain fuel on the island. So as we're wrapping up here, these some of the takeaways from this experience are, simplified screening methods are indeed simplified, and it's important to remember where they come from and their origins, and that they may or may not be applicable to the soils that you're looking at. The cone calibration for us was a fairly effective way to understand how our actual cone, our actual CPT was actually estimating a relative density. We also learned that despite your best intentions, testing and retesting and redoing and doing it over again, it is like being in grad school all over again. You get to try something and come back the next day and try it all over again because it didn't quite work the first time, and that doesn't always, or that doesn't change. And then, I'll say just that all coral sands are not equal. So make sure you do your homework at your site, because this may or may not be true for a site in Puerto Rico or other location. Let's see. Then I should throw in some acknowledgements here. Some of my co-workers, Andrew Daggett, Nick Moran, Josue Rodriguez, and Mark Musial, all in Golder, provided support for this project. And there is a nice bar in Kwajalein, so this is a shot from the bar as we'd finished up sampling all the soils and doing a number of days of testing out there. And so with that, I will come to the I guess conclusion of the presentation, and then open the floor up to questions.
Awesome. Thank you, John. That was a very nice presentation covering a lot of interesting stuff. So if anyone has any question, the floor is now open to the questions. If you don't have access to good audio, you can type your questions in the chat box, and I will happily reiterate your question to John.
I had a question. When you were doing deep soil mixing, how concerned were you about hitting some sort of explosive? Like, did you excavate the first 5 feet, or what was the precaution there?
Yeah, that's a great question. They actually they've constructed, I believe, 2 tank foundations now, and they did cut out the upper 5 feet of soil. Groundwater is at about 7 feet. So they cut out the upper 5 feet of soil so that they could cut down on the amount of drilling that they had to do, and that pretty much took most of the UXO out of the system. But one of the benefits of these large drill rigs, these going back to, we'll just go back here. These are 6 foot diameter deep soil mixed columns, and so with the equipment you end up not having anybody really that close to your drill spot. To my knowledge, they haven't actually hit any yet, but at least there's a lot of steel between the people that are drilling and the UXO if they do encounter it. So yeah, another good question. An interesting aspect to doing geotechnical work.
Thanks.
For the mini cone test that you did, I would actually expect to have higher stress concentrations near the tip and potential more issues with particle breaking. And so the correlation you're developing between relative density and penetration resistance based on the calibration chamber test might be in some way biased by the fact that you're using a mini cone. Was that in consideration at all?
Yeah, I mean that was, there was no real good way to to evaluate that, at least that we could effectively institute. One of the things that we did was we advanced a number of tests and sampled the soils right around where the tip had gone through, and done sieve analyses between the before and after, and we found very little difference, or the development or crushing of the material to suggest that we were changing the gradation, if you will, at least of that testing. So that we did think about that, and this was, and certainly open to other thoughts that you might have on ways to quantify that, but that was the best way that we could come up with, in a fairly reasonable fashion.
I think it is a good way. And no, I mean, you have limited abilities, because it's nice that you actually had a calibration chamber.
Yeah.
So I think you did a good job. So it wasn't critical.
Oh, no. Yeah.
And then another question, you went from a deep mix grid, which I like, to the deep mix columns. What was the motivation? Was that just economics?
Economics, and the contractor who's out there, they ended up starting with, and this is a whole nother story on its own, but the contractor, we designed the original deep soil mixing to be done with a cutter soil mixer, CSM.
Mm-hmm.
And the contractor that was low bid, because this is how these always go, right? They brought out a drill rig and a paddle blade to do their mixing, and so they were basically going to make these huge panels, really thick panels. And so this, I like the panel design as well, but this layout ends up being a little bit more conducive to the type of equipment that they ended up with on site.
Okay. Thank you.
And because we were moving to a static settlement issue rather than trying to mitigate liquefaction, this became a fairly reasonable approach as well.
A very interesting project. Thank you for the presentation.
Yeah, and the calibration chamber was an interesting piece to put together. Alaska doesn't have, we don't do a lot of CPT in Alaska. Oftentimes we have glacial tills and other materials that we're working with. And so we didn't have one of these just kind of sitting around. So we ended up fabricating one, basically coming up with our own design. If I go back, I'll just highlight some of we're working with a fab shop and a guy that's actually pretty sharp on kind of making stuff out of nothing. And what we ended up with was this aluminum structure, because with all that soil in there, this is actually a pretty heavy piece to move around. And we had an inner and an outer plate, and the inner plate was on the soil. And then there was a wheelbarrow tire that was in between the inner tube, between the top plate and the bottom plate. And what we ended up doing was inflating that inner tube to create our overburden pressure within the system. And so we didn't have a real fancy a fancy calibration chamber, but it seemed to do the trick. So,
John, to that effect, I also find the use of the calibration chamber very imaginative. How often is a solution like this envisioned in consulting? If you had asked me before, I would have told you that calibration chambers are done at universities, but not at consulting firms. But is this something that is done commonly?
So one of the real benefits, and I won't grandstand for Golder too much here, but one of the benefits of working for a larger geotechnical consultant is there are these opportunities. Golder has done a number of tests, calibration chamber tests for a few different projects, and it usually has got to be a project of some kind of scale to justify going down this path. And in the past, a lot of, like you said, with on the research side, we've worked with a number of universities to perform some of these calibration tests, calibration chamber tests. And so it's not, I would say it's not common at all within the consulting industry. It takes some fairly large scale projects to justify the use of this device, and oftentimes the consultant will work with a university who has a calibration chamber kind of sitting around to do that work. So this will probably be the only time in my in my life that I'll get to do something this this intricate. Maybe I shouldn't say the only time, but I don't see these opportunities walking in the door very often. So.
Thank you.
Yeah.
John, I'm kind of curious about the availability of equipment and materials on the island. So were they aware of the liquefaction hazard there before this project? Like, was deep soil mixing used for other projects already? Did they have the equipment there, or does it have to be shipped in?
So that's a great question. So as I showed in the early part of my presentation, the SPT pretty much predicts that that liquefaction is not an issue. And to my knowledge, our project was the first project on the island to actually push cone. And so, and it's not to say that there isn't, potential liquefaction at the island. It's just, lower than our initial CPT indicated. However, it was more of a head in the sand issue on Kwajalein, because they've been collecting all this data with SPT and running the numbers. Even with the large ground accelerations, they couldn't really develop a lot of liquefaction. So so this project was, in a way, a project that brought new light to some of the hazards on the island. And one of the quips that the Corps of Engineers said is, we should have never let you take the cone out there, because we wouldn't have had this problem. And my response is, well, the problem's still there, you just don't characterize it. So it's that's a good question. And I think that we'll probably see other studies on the island. I mean, there's that I mentioned the Space Fence program. There's a lot of money that goes to projects to support the space fence on this island, if an earthquake does happen, during the life of that, it will be interesting to see, what happens to some of those facilities. So,
Thanks.
Is there any other question? Because in the chat box, I think there are like some thanks from Professor Stork and Jose, but I don't see any questions in the chat box now. So if not,
I'll ask a question. Did you happen to think, did you do any shear wave measurements? Did you happen to get any, particularly seismic cone would be preferred for
yes,
for the
so,
liquefaction evaluation?
Yeah, maybe I should have. So we in our original program, we did a one CPT, a seismic CPT, and then when we did our second program, we actually did 5 more. And so we found that those results actually worked out fairly nicely and compared well with the Bender element results. So the seismic CPT was a good tool to have out there as well. So
within the correlation between the penetration resistance and the measured shear wave velocity, did it differ much from, say, a silica-based correlation? Were you getting much higher shear wave velocities than you would predict with just the cone directly?
They were higher. Yeah, they were higher than we would have predicted. Yep.
That would be a good indication that you have less liquefaction potential than the CPT would necessarily predict.
Yep. Yeah. Agreed. And for all you 1D soil modelers out there, I actually had a number of or some conversations with Dr. Hashash about modeling this in deep soil, and if he'd ever done any coral sand-based site response modeling, and his answer is no. So I'll dangle that carrot out to the crowd for interesting things to think about.
Okay.
Well, great. Thank you so much. I really appreciate the opportunity to sit down with you today and talk about this project.
Yeah, thanks
Thank
for
you, John.
coming to our chapter.
Yeah, thanks, John. This was really great.
Thank you.
Thank you.
All
Have a
right.
good day. Stay warm and powered up. So
Yes, and hopefully we'll see some of you 20 minutes or so for the meet and greet. Thanks again, everybody.
Yeah.
Bye.
Bye.
thanks.